The FitzHugh-Nagumo model is a simplification of the Hodgkin-Huxley model that reduces the complexity of the Hodgkin-Huxley model into a two-variable system that describes the electrical activity of neurons. In these equations, U is the voltage of the neuron, I is the current, and W represents a recovery variable that explains both the inactivation of sodium channels, preventing further excitation, and the activation of potassium channels, helping to repolarize the membrane. Just for simplicity, we will look at a piecewise version of it to understand its dynamics. The first thing we need to do is find the nullclines. Along the nullcline, the derivative of U is 0. This allows us to find the following. Similarly with W, along the nullcline, the derivative is 0, which helps us find that W is equal to BU as our W nullcline. Now, let's plot the nullclines and substitute within each quadrant arbitrary values to understand the trajectories in our system. I will be doing this for I is equal to 6, and then we'll see the other cases. Now this would look somewhat like the following. As we can see, the overall form of the flow will be that of a spiral. Let's try and study the stability of our fixed point in order to better understand how our system behaves. To do this, we use the Jacobian to study the stability of our fixed point upon an approximation of a linearized system. This will look something like this, where J1 is the first and third pieces of our FitzHugh piecewise equation, and J2 the second section of it. Solving the eigenvalue problem for both yields the following. For J1, if B is more than 0, then lambda is complex with negative real part. So the fixed point is a stable spiral. For J2, the discriminant can be positive or negative, meaning that lambda can be real or complex. However, since the real part of lambda is equal to 1/2 of P minus 1 is bigger than 0, the fixed point will always be unstable. Having understood that, let's see how our system behaves. Let's go back to our example of I is equal to 6, where we would expect to see an unstable fixed point. As we can see, something weird happens. There's an inward trajectory, but it almost finds itself oscillating at a certain value. What is happening is what's known as a limit cycle. There's a closed trajectory in a dynamical system where the system's state evolves periodically over time. In our case, nearby trajectories spiral out towards the circle and then stay there, and they oscillate with a specific t period. If you ask me, I would say that's pretty amazing. And as you can see, the U values also see themselves reaching this oscillation. And you can see how understanding the phase plots can give you some very good intuition into how your variables are developing over time. Now, if we look at other cases where I is equal to 0, the fixed point will be stable, so the trajectories all reach that point. Similarly, with I is equal to 10. Now that we have understood that, I will leave you to enjoy some nice animations of how different values of I lead to different ways that our system will be developing and evolving. So hope you enjoy, and thanks for watching.